In our last chapter, we were looking at the electronic structure of atoms. We looked at where those electrons are in a ground state atom, and we put them in the 1s, the 2s, and so forth. We also looked at, once we had that complete, how that electronic structure tied into the periodic table, and we could get those valence electron numbers off the periodic table. We saw that the noble gases over on the far right-hand side were the most stable of the electron configurations, and atoms that were close to those noble gases were highly reactive as they tried to gain or lose electrons to become like the noble gases. In this chapter and the chapter to come, we're going to start focusing in on the structure of the electrons for molecules or compounds, whether they be ionic or covalent. So let us look at this introduction here. We're going to be focusing on what's called Lewis theory with this chapter. So we're going to introduce ourselves to bonding, what holds those molecules and ionic compounds together, and look at it in terms of the electron structure. Throughout this chapter, we're going to be looking at how they're bonded together. We're going to be focusing in on 3 bonding theories. We'll start with this chapter, and that's Lewis theory. Once we look at Lewis theory, then we'll be able to look at valence bond theory, and then lastly, we'll look at molecular orbital theory. So these are all different ways to think about how compounds form within their electronic structure, and they're different ways of looking at it depending upon what you're needing to know. So let's kind of summarize the different types of bonding that we know about at this point. The first type of bonding that we are going to look at is going to be ionic bonding, and we'll focus on that in this lesson. We learned prior to this chapter that ionic bonding occurs between metals and nonmetals. So we have an example here of sodium chloride. So table salt would be an example of that. We have a metal and a nonmetal, and that's really all we focused on in previous chapters about it. We talked about how this is formed by the transfer of electrons. The sodium, with its valence electron, would like to lose that valence electron, become a cation, and the chloride, being right next to the noble gases, would like to gain that electron to become an anion, so we transfer those electrons. So that's why they're trying to get that noble gas configuration. The metal really doesn't want the electron. It is easy to remove. The chlorine really has a high electron affinity, so it wants that electron. Covalent bonding is the other type of bonding. Now, when we talked about covalent bonding before, we talked about it as only between nonmetals and nonmetals. We talked about how this is a sharing of electrons that occur to form a covalent bond. Now, we're going to be looking at why they share electrons as we go into this, but what's happening here is we have a nonmetal that wants electrons to get to a noble gas configuration, and another nonmetal that wants the electron in order to get a noble gas structure, and so they have to share those electrons, and we will be looking very closely at that sharing as we look at Lewis theory. There is a third type of bonding that we really did not talk about, and I'm only going to briefly mention here, and that is metallic bonding. When metallic bonding occurs, it does not form a compound, and that's why we didn't talk about it. We talked about compounds, ionic compounds, and covalent or molecular compounds, but there is a type of bonding called metallic bonding. It occurs between metals. It does not form a compound, and that's all we're going to really need to know about that right now. It is something that we will look at eventually. So our use of Lewis theory has to utilize something called a Lewis dot symbol. And here's the definition of a Lewis dot symbol. It shows the symbol. So we see, potassium is a K, but it also shows the number of valence electrons as a dot. So here we have hydrogen. We know that everything in this group here has 1 valence electron, so they're showing it as 1 dot. The 2A family has 2 valence electrons, and we see it as 2 dots, and notice how they're separated. The 3 has 3 dots, and so forth. Now, the only thing that's really unusual about what we see here is you notice these guys here in this family have 2 dots, but they're spread apart. Helium is shown to be unique in that they put the 2 dots next to each other, and the reason for that is those electrons fill up that 1s shell, and they cannot get involved in bonding. And these that are spread out, yes, they're still filling up the S shell, but they can get involved in bonding, and so they're spread out. Okay, so let's focus in on ionic bonding using this Lewis theory, okay? That's our first kind of bonding that we want to focus at. So what is an ionic bond? An ionic bond is an electrostatic force that's holding cations and anions together. That's what the bond is. A bond is described by what is the force that holds those atoms together, and in the case of an ionic bond, this is an electrostatic force. Remember, that is just a sophisticated way of saying opposite charges attract each other, and that is what's holding an ionic compound together. So what we're going to do is use Lewis dot symbols to show the formation of those ions, and then that electrostatic force will just be the natural outcome of that. So we're going to begin with looking at using Lewis dot symbols. We're going to have a lithium, and we have one valence electron, so I'll put that as a dot, reacting with fluorine. Now, if you look at a periodic table and you look at how many valence electrons fluorine has, it has 7 valence electrons. So I will put the 7 valence electrons around. Usually we spread them out, 1, 2, 3, 4, 5, 6, 7. Then we start pairing them up. So those are the Lewis dot symbols of the elements that make up lithium fluoride. What happens when you form an ionic bond is the lithium doesn't want the electron and will donate it to the fluorine. So we show that donation as an arrow, okay? So once that happens, what do we have? We have lithium that has lost that valence electron, so it's going to have a plus charge, and we have fluorine that has gained that electron. So now it has the 8 valence electrons, and it will have a minus charge. Now we have a positive charge and a negative charge. They will be attracted to each other, and that's an ionic bond, an electrostatic charge, electrostatic force attracting between the cation and the anion. Well, let's do another example. Let's do an example of lithium and oxygen, okay, and form the ionic compound for that. Now, lithium we know has 1 valence electron, so I'll draw that 1 valence electron. If you look at oxygen on the periodic table, then we'll see that it has a 6 above it, so it's in the 6A group, so we'll put 6 electrons around it, okay? So we have its 6 electrons around it. Now, the lithium doesn't want this electron, so it will donate its electron to the oxygen. But this is not quite where it wants to be yet. Oxygen doesn't want to have 7 valence electrons. Oxygen would like to be like the nearest noble gas and have 8 valence electrons. So we would have to have another lithium with its valence electron giving its electron to the oxygen. At that point, both of them can be happy, or all 3 of these atoms can be happy. Lithium lost that 1 valence electron. The other lithium lost that 1 valence electron. So we have 2 of these. And we have the oxygen, and now it gained 2 electrons, so it has 8. And if you've gained 2 electrons, you will have a 2 minus charge. So this shows what we knew about lithium and oxygen if they have from where they were on the periodic table. Way back in Chapter 2, we learned how to write good formulas for ionic compounds. But at that point, we were just looking at a periodic table and seeing where lithium was and knowing that lithium had a plus charge, and looking at where oxygen was and knowing that it had a 2 minus charge, and we did a kind of a crisscross thing and came up with Li2O as the formula. But this is what's happening with the electrons. So Lewis theory shows the electrons and playing their role in how they move in order to form your ionic compound. Okay, so when you have this electrostatic attraction, you form a lattice structure, okay? So a lattice structure is what we see on the screen with the picture on the right there. That is the ionic compound with sodium ions, which are represented here with the bluish purple. These are your sodium ions. These green are your chloride ions. And we know that ionic compounds have this lattice, this 3-dimensional structure. Well, there's this thing called lattice energy, and the lattice energy is the energy released when these ions come together to make the ionic compound. All right, so it's the energy released when forming a crystalline lattice. That's a crystalline lattice. C-R-Y-S-T, crystalline lattice. That's what this is over here on the right. As those ions are being formed, they will then be attracted and they will come together and they will form that lattice from, what are they being formed from? All of these are their ions in the gaseous state. So this is a chlorine minus gas ion. This is an Li plus gas ion. They are in the gaseous state and then they come together, and we see all these arrows representing it coming together to form that. So when you look at the definition of lattice energy, what I want you to stop and think about is what would have to be the sign of lattice energy, and we use LE to represent that. What would have to be the sign of it? So you have to think back to chapter 6. We have to think about that word released and what would be the sign of that value. Well, hopefully you said since it's released, it is exothermic, and exothermic is negative. Now here is a table full of lattice energy. So if you picked ahead, you'd seen all these negative values here in your notes. All of them are negative because it is the energy released when the ionic compound comes together. So we see not only lattice energies provided in this table here, and we have various ionic compounds, we have their lattice energy, but we're also seeing the melting point being given to us. So I want you to kind of just look at this, and I want you to try to see any kind of trends that we can come up with. So you've got that in your notes, and as you look at that table, I want you to determine which one of these statements you see. That the bigger the charge on the ions, the greater the lattice energy release, the more negative the value, in other words, or the smaller the charge, the greater lattice energy released, meaning a bigger negative number. So look at that language, greater lattice energy released, it's negative, I'm looking for a big negative value. Which one is going to lead you to that, the larger charge or the smaller charges? Well, you should have picked A, the larger the charge, the greater the lattice energy. If we look back at our table once again, what do we see here? Charges. Lithium has got a +1 charge and fluoride has a -1 charge. All of these from here to here are, actually all the way down to here, are +1 cations with a -1 anion. Now we have a +2 cation with a -1 anion. That's here and here. And here we have a +2 with a -2. So what is happening here? Now this has got an issue, doesn't it? That's a problem. We've got a positive value being listed there. I think it's missing a minus sign. So put a minus sign in your notes if it wasn't there already. I think that's where it's run off to. I think it's right down there. Anyway, we have got kind of an oddball here, but for the most part, what we're seeing is with the +1 and -1 signs, these are all smaller than when we start getting +2s and all the way up to -2s. So we don't have they're not listed in order of increasing, but we definitely have a bunch of smaller numbers here, and then they get bigger as the charge gets bigger. So that's one of the trends that we see there. Now Coulomb's law is a law that drives electrostatic forces. When you have an attraction between opposite charges, that is Coulomb's law. Now you won't do mathematical work with Coulomb's law, but you need to look at the components and you need to see what it is telling you about a lattice energy. Okay, so it's an electrostatic attraction here, and as those guys come together to form our ionic bond and form our ionic compound, it's going to release energy. There's two things playing out here. There's Q and there's R. What Q is a symbol for charge. It is the magnitude of the charge. So we've got plus charges, and we have negative charges, but their magnitude is what Q is. And R is the distance of separation between the charges. So once you form that electrostatic attraction between the cation and the anion, that distance between those ions is what R is all about. Now what this equation is telling me is that there's two main factors that are affecting our lattice energy. Okay? The first factor is the bigger factor. Okay? It's the first thing you want to look at, and that's the size of the charge. That's what I wanted you to look at with the table. As you looked at the table, you saw that when the charges got bigger, the lattice energy was bigger, meaning more negative. When the charges were smaller with plus ones and minus ones, like our lithium and our fluorine, those smaller charges led to smaller lattice energies. So when you're comparing ionic compounds, and here's two ionic compounds, lithium with a plus one, minus one, and fluoride with a minus one, or lithium with oxygen where we have a plus one and a minus two, the bigger the charge, the greater the lattice energy is going to be. The more negative energy is going to be released. Okay, the second thing then we look at is then the size of the ions, okay? Because the size of the ions is going to determine how closely these guys get together, okay? And that is the R part, okay? So the R part sits in the denominator. The smaller the ions they are, the smaller those ions are, you're putting a smaller number in the denominator. If you're putting a smaller number in the denominator, you're going to have a greater lattice energy. So I'm going to be asking you eventually to look at ionic compounds and decide which one's going to have the greater lattice energy. And you're not going to be looking at that table. You're going to only be looking at the periodic table, which will get you the charges, or looking at the periodic table to get the size, relative size of the ions. And then you're going to use those two statements that you see there to rank things according to their lattice energy. So you have to remember those. Time and time again, I'll have students come back to me and say, I don't know how to do this problem. And this slide just kind of, they look at it and they think they're done with it. But know that you have got to know these two things affected in that order. You first look at the size of the charge, and then when you're comparing and the charges are the same, then you will whittle down and look at the size of the ions. So let us look at the comparison by looking at that table. So you're going to go back again and you're going to look in their notes at your table, and you're going to see if you can see a general trend. That's not a perfect trend, but a general trend between lattice energy and MP. My MP stands for melting point. So look at your table and see if you can see a connection. All right, so what you should have seen is B. Why? Well, let's look at the table. Let's see if I've got that table here. Let's look here. Here are the guys with a general small, S-M-A-L-L, small lattice energy, okay? And look at the size of their melting points. Then we've got these guys that have a larger lattice energy, and look at their melting points, okay? Now what does this mean? This means that it doesn't melt, it just keeps on getting hotter and hotter until it sublimes, turns directly into a gas. So that's a high temperature there. In general, these are higher than those. Now if we whittle down inside of here, and let's do some comparisons down on this level, we've got our larger negative lattice energy here with a larger melting point. Pick one of the smaller ones. Here's a smaller one, and it has a smaller melting point. So that is the general trend that we will see there between melting point and lattice energy. What I will end up asking you to do sometimes is look at an ionic compounds and say which one's going to have the greater melting point and which is going to have the lower melting point. Whenever you're comparing ionic compounds, that's what you're going to be looking at. To decide which one's going to have the higher melting point and lower melting point, you're first going to think about which one's got the greater lattice energy, meaning more exothermic, greater negative value, and the one that has a greater negative would have the higher melting point. So you have to keep in mind that trend that you see right there. All right, so we're going to practice doing that. So don't look at the lattice energy table to do this. And some of these are not even in there that I'm going to give you, so you couldn't look at it anyway. But you want to train yourself into being able to figure out which one is going to be the lowest melting point, which one's going to be the highest melting point. So these are your 4 ionic compounds that I have got listed up here. You're going to look at a periodic table, you're going to figure out their lattice energy connections and then their melting point connections. And let's see how you can do with this one. Well, you now know what the correct answer is. This is the correct answer, but maybe you struggled with getting to this point. Let me tell you how I would have thought through the process. The first thing I would have done is gone through and done the charges of everything, because the charge plays the biggest role with lattice energy and thus the melting point. Magnesium has a +2 charge, chloride a -1. Lithium has a +1 charge, chlorine a -1, sodium a +1, chlorine a -1, calcium +2, chlorine -1. So we've got our charges there. Now the next thing I would do is realize that the bigger the charge, the stronger the lattice energy, and I would pick these two guys to be down here. So the 1 and the 4 are going to be greater than the 2 and the 3. So I know that they have a stronger lattice energy, therefore they're going to have the higher melting point. But that doesn't fine-tune it. To fine-tune it, we need to look at the size of the ion itself. So we look at a periodic table, and when we're comparing, let's say, the 2 and the 3, okay, as we're comparing those, we have the chlorine that's the same, but it's the sodium and the lithium ion that are different. This one is smaller. It's higher on the periodic table. This one is larger. And we remember that in the Coulomb's law, the size is in the denominator. So the smaller the size, the greater the lattice energy is going to be. Therefore, I would know that the lithium one would be stronger attraction, therefore a higher melting point. And that's why I would put the lithium before I would put the sodium. Now I do the same thing with number 1 and number 4 here. I'm looking at where they are on the periodic table. Okay? Magnesium is higher on the periodic table, therefore it is smaller. And the calcium ion would be larger. So we would put the calcium in terms of melting point. It has a weaker lattice energy, less negative, than the other one that's smaller. It would have a greater lattice energy, and so that is why I would put them in this order. So you first look at this, just the charges. Then you fine-tune between these two by looking at the size of the ion. Okay? Fine-tune between these two by looking at the size of the ion. All right, so we know what lattice energy is. We can define it. We know lattice energy is the energy released when you are bringing these ions together to form an ionic compound. So there is a release as they come together. We know how to rank lattice energy by looking at the size of the ions. We know how to rank lattice energy then by looking at, the charges. I said ions. You're first going to look at the size of the charges, and then you're going to look at the size of the ions, and you can make a ranking based upon that. All right, so this concludes our lesson on ionic bonding and lattice energy.